Hi everyone. So lesson 2.4, building on what we've done so far, including our last lesson with integration by parts, we're going to look at another method that can solve very complex integrals. So we're going to look at functions that have a lot of terms in them. Specifically, x squared, x cubed, terms like that. Okay, so this is moving kind of away from having, the sine, cosine, exponential functions. So we have a function like this, the integral of 7 minus x divided by x squared plus x minus 2 dx. All of these individually are easy integrals. The integral of 7, okay, 7x. If you had the negative x, the integral, of negative x would be negative 1 over 2x squared. So all of these are simple integrals by themselves, but when you put them into one large integral, okay, suddenly we don't have a good method to integrate that with the tools, I should say, that we've learned so far. So what we're going to do, okay, I'm going to teach you a method. This is lesson 1 of 2. And the method is going to use partial fractions. So what we're going to do is we're going to turn this into multiple smaller fractions, or what we call partial fractions, okay, that are easier to integrate. So what I'm going to show you in this method is how to turn that equation into these two partial fractions, 2 over x minus 1 and 3 over x plus 2. I'm going to show you how to do that. And when we get to these easier functions to integrate, we know that anything divided by a function, we can simply, the integral involves ln. Okay, so it becomes a much easier way to integrate that function. All right. So I'm going to give you several steps that you have to take, and I'm going to walk you through each step. Okay. The first step is to make sure the degree of the numerator is less than the denominator. When I say degree, I mean if you have in the previous example, okay, when we had 7 minus x, so the highest order function in the numerator is x. Okay, so that means that in the denominator, the lowest order we could have, we have to have at least an x squared term. Okay, so you have to have the order of the, or the degree of the denominator has to be higher than the numerator. So I'm telling you that because if you don't, then you have to actually divide them first. And I'm not going to do that in these examples. So that's why I put this big hint here. So I'm always going to make sure that this is the case, but I want you to know that that is kind of the first important rule if you got into more advanced versions of these functions. The next thing that you have to look at is if you have an equation, let's say you have 7 minus x, which is what we had in the previous example, and then you have items in the denominator, okay? X squared, let's say, plus 3x minus 2. The next thing you want to do is you want to factor everything here in the denominator. When I say factor, if you remember back from your previous math class, that means factoring it to look like this. X plus 2 and x minus 1. So turning that quadratic into multiple factors. And I know some of you listening to this are probably thinking, I don't remember how to factor. So I'm going to give you a crash course in factoring on the next slide. I also have a full lesson posted on factoring, so I will give you the link to that as well if you want to watch for a full refresh. So let's first now talk about factoring. Okay, so this second step in the process is to factor the denominator. Oftentimes we're going to have something like this equation here, x squared plus 9x plus 20. That is called a trinomial, and it's a trinomial because it has 3 terms. Okay, a monomial has 1 term, a binomial has 2 terms, and a trinomial has 3. So a monomial would be something like 3x, binomial would be 3x plus 5, okay? And this is an example of a trinomial, okay? So if we start with an equation like this, x squared plus 9x plus 20. If we're going to factor it, there's two key items you have to keep in mind, okay? First thing you have to look at is the constant, okay? There's always going to be a constant. If there isn't and there's an x here, then you simply would be able to factor an x out, okay? So there's always going to be a constant. Now you have to think of what the factors are. The two numbers, when put together, will multiply to give you, in this case, positive 20. So I've written them all here. Plus 1 and plus 20 will give you positive 20. Plus 4 and plus 5 multiplied together would give you positive 20. Plus 2 and plus 10 would also give you positive 20. And then their negative equivalents, because a negative times a negative is a positive number, would also give you positive 20. So what you do is once you've found those factors, you have to then add them up, okay? And the sum of those factors has to be the same as the coefficient behind this middle term with x, okay? So looking at this second column, adding them up, positive 4 and positive 5 works because it gives you positive 9, okay? So what you do with that is you simply translate it into an equation like this. X plus one of the factors, so in this case x plus 4, multiplied by x plus the second factor, in this case, which is 5. So you can check whether that works using what's called FOIL, okay? And what FOIL means is you multiply the first terms, that's the f, which would be x times x is x squared. The outside terms, which would be x and 5, which gives you 5x. The inside terms, which would be 4 and x, which gives you 4x. And the last terms, okay, 4 and 5, which gives you 20. So this is for checking your work after to see if you factored properly. But if you did, then you should get the same answer as the one that's sitting here, okay? So that's the brief overview on factoring. Again, I will post the link for a full video I did for a different class as it relates to factoring, okay? So let's look moving to step number 3. So I'm starting with the exact same piece, all right, the exact same integral that I had on the very first slide of this lesson. 7 minus x divided by x squared plus x minus 2. So I know using factoring, okay, the numbers that add up or multiply to negative 2 and add up to positive 1 are plus 2 and minus 1. So that means that my factors here are x plus 2 and x minus 1. So now that you've written it in this form, okay, where it's factored as much as you can, then you now use that to determine your partial fractions. Okay, in this case, I have all terms that just have x. We'll get into in the next lesson what happens if you can't factor one. So let's say you have x squared plus 4x plus 7. Okay, you can't find two factors of 7 that add up to 4, so you can't factor this anymore. It's already there. So we'll talk about that in the next lesson. So assuming you can factor it to this point here, what you do is you set 7 minus x divided by both factors, x plus 2 times x minus 1, equal to two separate fractions or partial fractions. Okay, one divided by the first factor, so x plus 2, and the other divided by the second factor, which is x minus 1. So you can see factor 1 and factor 2. Now you don't know what these values need to be. That's what this method will determine. So we just set them as a and b. Okay? So now that we know what our factors are and what the basic setup is for partial fractions, we need to figure out what a and b are, right? So then once we have that, we have what this is equal to in these two simpler fractions that we know how to integrate. So the first step is you always have to remove the fractions. Okay, so all the terms in the denominator. And we do that because we notice that x plus 2 and x minus 1, okay, are the only two factors. So if we want to make sure we remove everything from all of the fractions, we multiply both sides by x plus 2 and x minus 1. So it's always going to be multiplying it by all of the factors. And when you do to one side of the equation, you have to do to the other side. So what that will do, you'll notice, is on the left-hand side, it cancels out all of the factors in the denominator. So you're left with just 7 minus x. On the right side, it's a little bit different. Since you're multiplying by two factors, you'll notice for a that it cancels out. Okay, you see it cancels out the x plus 2, but not the x minus 1. So we're left with a times x minus 1. For the b term, you'll notice it cancels the x minus 1, but not the x plus 2 term. So we have plus b times x plus 2. Okay? So the way we can approach this is we can either look at it, and at this point we need to solve for a and b. So we can do that by substituting in values of x, should we choose to. So we could do, for example, you pick the x values here that correspond to these factors. So those x values are x equals 1 and x equals negative 2. So if we substitute those in, one of those terms will automatically be 0, and we can solve. In our next lesson, I'm going to show you a different way to do it when we get into more complicated versions. So I'm going to start by substituting x equals 1. And if I do that, I get 7 minus 1 equals a times 1 minus 1 plus b times 1 plus 2. So you can see here, by substituting in 1, we're removing this whole factor because we're left with 1 minus 1, which is 0. So a is now gone. So we have 7 minus 1, which is 6, and that now equals 3 times b. Okay, that's just adding up the 1 plus 2. So solving for this, we divide both sides by 3, and we get that b is equal to 2. Okay, so we know that b is 2. Now we can solve for a. Okay, so we have 7 minus x is equal to a times x minus 1 plus, now we can substitute in for b, 2 times x plus 2. So the next factor we can substitute in, we've just done x equals 1. We can now do x equals negative 2. So if we substitute x equals negative 2, we get 7 minus negative 2 is equal to a times negative 2 minus 1 plus 2 times negative 2 plus 2. So you can see again, it doesn't matter which one we substitute in first, because whatever one we substitute will either 0 the a term or the b term. In this case, we have negative 2 plus 2, which is 0. So this term will just go to 0. So 7 minus negative 2 gives us 9, and that's equal to a times negative 3. So to solve for a, we now have to divide both sides by negative 3, and we get that a is equal to negative 3. Okay, I'll write it over here. Okay, so knowing those two values, we can now write the two partial fractions. So if we write them, we'll get negative 3 over x plus 2 plus 2 over x minus 1. So now we know that we can substitute this in instead of this big expression in the integral. Okay? Okay, so instead of this function, 7 minus x over x plus 2 times x minus 1, we found the equivalent fractions. So we can write that instead as negative 3 over x plus 2, substituting in the value for a, plus 2 divided by x minus 1, substituting in the value for b. So remember, we had the integral of 7 minus x divided by x plus 2 and x minus 1. That instead can be written as integrals of these partial fractions. So we have the integral of negative 3 over x plus 2 plus the integral of 2 over x minus 1. Remember, for integrals and derivatives, if they're added or subtracted together like this, you can treat them as either separate integrals in this case, or remember when we had terms like x squared plus 2x, you took the integral of each of these pieces separately. So the next item I'm going to do is when you have a constant in the integral, you can move it outside of it. So this is the same as negative 3 times the integral of 1 over x plus 2 plus 2 times the integral of 1 over x minus 1. So these integrals are ones that we've seen before. Remember, the integral of 1 over some function u du is equal to the ln of the absolute value of that function that was in the denominator u, okay, and plus a constant. So in this case here, we've got two functions that are set up that way, okay? The first one being 1 over x plus 2, and the second one being 1 over x plus 1. So we can write these as negative 3 times the ln of x plus 2 plus 2 times the ln of x minus 1, okay? And then at the end, we can add our constant. So you'll see in partial fractions, when they're set up with terms like that, x minus 1, x plus 2, x is to the exponent 1, you're going to get in your final solution the ln of one of those partial fractions. Okay, so just something to keep in mind as we start looking now at a few examples. Okay, so now that I've shown you the method, I'm going to go over 3 more examples. And what you're going to see in these examples is that the process that I follow is the same every single time. Okay, for all of these cases you're going to see with partial fractions. When we get into more advanced examples in the next lesson, you're going to see that the process largely remains the same. There's just small tweaks. Okay, so it's important to understand the steps that I take when I solve these problems. So this question says to evaluate the integral of 3x plus 2 divided by x squared plus x. Okay. Remember, we're going to have to use partial fractions for this type of function. So our first step is to make sure that the degree of the numerator is less than the denominator. So in the denominator, we have a squared term. In the numerator, we have just an x term. So that means that it's a second order equation in the denominator and first order in the numerator. Again, I won't test you on questions that don't have that automatically, but it's still a good habit to get into. Our next step is to factor it. Okay, so factor everything in the denominator. So we can write this as 3x plus 2 divided by, you can see we have an x common to both terms. So we can factor out that x and we get x plus 1. Okay, so you'll see that we can't factor that anymore, right? There's no way we can possibly factor anything additionally. So we see that we have two factors here. So what that means is we can rewrite this as 3x plus 2 over x times x plus 1 has to equal a divided by x plus b divided by x plus 1. Okay, which each of those denominators being just one of the two factors that's sitting here. So now, following the same pattern, we take all of these variables and we multiply both sides by it. So we multiply it by x and x plus 1. Okay, so both factors sitting here in the denominator. On the left-hand side here, you'll see that the x plus 1s and the x cancel. So we're left with just 3x plus 2. On the right side, the x's will cancel for the a term, but we're still left with a times x plus 1. Okay. For the b term, we'll see the x plus 1s cancel, but not the x. So we're left with just b times x. So we can see here that the two factors that will zero these terms are when x is 0, the b term will go to 0. And when x is negative 1, the a term will go to 0. So we'll start with the 0, okay, left to right. So we have substitute in x equals 0. We get 3 times 0 plus 2 equals a times 0 plus 1 plus b times 0. So we're left with just this one cancels and this one cancels. So we're left with just 2 equals a. So pretty straightforward. Now we'll substitute in x equals negative 1. So if we do that, we get 3 times negative 1 plus 2 is equal to 2, because I can substitute in the value for a, times negative 1 plus 1, plus b times negative 1. You can see this term will cancel anyways, because negative 1 plus 1 is 0. And we're left with negative 3 plus 2 is negative 1, and that's equal to negative b, or b must be equal to 1. So what this means is now we have our partial fractions, okay? So we can rewrite this as, instead of 3x plus 2 over x times x plus 1, we can rewrite this as negative, as the a term, 2 over x, minus, plus the b term, which is 1 divided by x plus 1, okay? So if I look at the integral, that means instead we have the integral of 2 over x plus the integral of 1 over x plus 1. And again, you see, since these terms are first order, so just x, they're always going to have integrals at the end that involve ln, okay? So if we find the integrals of these, remember, the integral of 1 over a function u du is equal to the ln of that function u, the absolute value, usually plus a constant. So if we find the integral of these, the integral of 2 over x dx is equal to 2 ln of x, again the absolute value, plus the second integral is just the ln of x plus 1, okay, again the absolute value, and then obviously at the end we add a constant, okay? So I hope after seeing a second example that you're starting to see the pattern with these, okay? The steps are always the same, and usually if they're first order x plus 1, 3x plus 2 in the denominator, we will end up at the end with some functions of ln, all right? Okay, so let's look at our next example. Evaluate the integral of 9 minus x divided by x squared plus 2x minus 3, okay, dx. So first thing we notice, all right, the numerator has just an x term and the denominator is x squared. So we see that the denominator is a higher order than the numerator. Next we see that we have to try and factor the denominator. Okay, and we can do that because x squared plus 2x minus 3, okay? So the factors, okay, that multiply to negative 3 are, let's do positive 3 and negative 1, or positive 1 and negative 3. Remember, keep in mind, they have to add up to positive 2. Well, plus 3 and negative 1 gives us positive 2, and positive 1 and negative 3 gives us negative 2. So these are the correct factors, positive 3 and negative 1. So substituting those in, this integral becomes the integral of 9 minus x divided by x plus 3 times x minus 1. Okay? Now, knowing we have those factors, we can use partial fractions. So this becomes 9 minus x divided by x plus 3 times x minus 1 has to equal a divided by the first factor, x plus 3, plus b divided by the second factor, x minus 1. Now, just like we did in the past, we're going to get rid of these fractions. And to do that, we're going to multiply both sides by all of these factors, x plus 3 and x minus 1. Okay? So on the left-hand side, the x plus 3's would cancel and the x minus 1's will cancel. So we're left with just 9 minus x. On the right-hand side for a, the x plus 3's will cancel, but the x minus 1's will not. So we're left with a times x minus 1. For b, you'll see the x minus 1 will cancel, but the x plus 3 will not. So we're left with b times x plus 3. Okay? So again, for this question, now that we're here, we need to solve for a and b, so we can start substituting in values. And the two values to use are the two factors of x that will give a 0. So the first one is that when x is 1, you'll have a term is 0. And when x is negative 3, sorry, that's a bad negative 3, let me rewrite it. When x equals negative 3, the b term will go to 0. So we'll start with x equals 1. We get 9 minus 1 is equal to a times 1 minus 1 plus b times 1 plus 3. So you can see the 1 minus 1 is a 0, so that term will cancel. And we're left with 9 minus 1, which is 8, is equal to 4b. So dividing both sides by 4, we get that b is equal to 2. Our next item is to substitute in the second factor, which is x equals negative 3. So if we substitute x equals negative 3, we get 9 minus negative 3 is equal to a times negative 3 minus 1 plus b, which we can now substitute in, as 2, times negative 3 plus 3. So you'll see with negative 3 plus 3, those will cancel. What we're left with is 9 minus negative 3 is the same as 9 plus 3, because it's double negative, so that's 12. That's equal to a times negative 3 plus 1, which is negative 4, so negative 4a. So dividing both sides by negative 4, we get that a is equal to negative 3. Okay? So what this means is that we can rewrite our integral as the integral of a, negative 3, over x plus 3, plus b, which is in the integral of 2 over x minus 1. Okay? Replacing the 9 minus x term, okay, that you can see in the integral, with the equivalent partial fractions. So now again, we can take the integral of these easily, knowing that the ln function, so the integral of 1 over u du is the ln of u, okay, the absolute value. So if we do that, we get negative 3 times the ln of the function in the denominator, x plus 3, plus 2 times the ln of x minus 1, and then obviously plus a constant. Okay? Okay, so our third example, our denominator looks a little bit different here. So we have evaluate the integral of 2x squared minus 5x minus 7 divided by x cubed plus 2x squared minus x minus 2. So you can see we have a cubed function in the denominator. And we're going to approach factoring a little differently. You'll kind of see somewhat similar methods. But our first step, we see that in the numerator, the highest order function is squared. In the denominator, it's cubed. So we're good for our first step. Again, I won't test you on any questions that don't have that, but good practice. Next, we need to factor the denominator. Okay, so we have the integral of 2x squared minus 5x minus 7 divided by. You can see here that I'm going to try grouping them. So the first two terms have an x squared in common. So I'm going to try factoring out the x squared. So I'm going to get x squared times x plus 2. And you can see we're close. The second term has an x minus 2. So I'm going to factor out a negative 1. So I'll do minus 1 times, and now this becomes positive x and positive 2. So x plus 2. So that means that we can factor this by factoring, I'll do it in a different color, factoring the x plus 2 out of both of these. And what we're left with is 2x squared minus 5x minus 7 divided by x squared minus 1 times x plus 2. So we can go one step further on this. X squared minus 1 can actually be factored further, and that's because it's what's known as a difference of squares. Okay? Again, I can show you more of this in my separate factoring video, which I will include the link to when I post this lecture. If we use difference of squares, x squared minus 1 becomes x plus 1 and x minus 1. Okay? What this means is if you have two terms that are squared, so x squared, okay, is the same as x to the exponent 2, 1 is the same as 1 squared. And where it says difference, that means that they're subtracted by one from another. Okay? And they can always be factored in this manner that I show. So what we're left with, fully factored, is the integral of 2x squared minus 5x minus 7 divided by x plus 1, x minus 1, and x plus 2. So the method of solving this is still the same as what we did in the past. So we set that equal. So we've got 2x squared minus 5x minus 7 divided by x plus 1, x minus 1, and x plus 2. We still set it equal to all of the individual factors. In this case, we have an extra one. So we have a divided by x plus 1 plus b divided by x minus 1 plus c divided by x plus 2. So the same thing that we did in the past, we now need to remove the items in the denominator. And we do that by multiplying both sides, okay, by all three factors. So we're going to multiply by x plus 1, x minus 1, and x plus 2. So if we do that, all right, then on the left-hand side, these will all disappear. And we're left with just 2x squared minus 5x minus 7. And that's going to be equal to, for a, okay, you can see that only the x plus 1 cancels. The remaining 2 will stay. So we have a times x plus 1, sorry, x minus 1, the remaining one, x minus 1, and x plus 2, plus b, and you'll see that the x minus 1s are the only ones that cancel. So we're left with x plus 1 and x plus 2. And for c, you can see that only the x plus 2 term will cancel. So we're left with x plus 1 and x minus 1. So I'm going to leave it, all right, factored like that. And you'll see why in a second. So just like we did in the previous two examples, plus when I introduced it, we're looking for the factors that will set some of these terms to 0. And there's 3 of them this time, right? Because we have an x plus 1, an x minus 1, and an x plus 2. So our factors, therefore, are x equals negative 1, x equals positive 1, and x equals negative 2, all of which will turn one of these to 0. So we can start with any one of them. I will start with substituting in negative 1. If we do that, we get 2 times negative 1 squared minus 5 times negative 1 minus 7 is equal to a times negative 1 minus 1 times negative 1 plus 2 plus b times negative 1 plus 1 and negative 1 plus 2. You can see the negative 1 plus 1 here will cause this term to cancel. And we'll have plus c times negative 1 plus 1 and negative 1 minus 1. Again, with a negative 1 plus 1, which is 0, this term will also cancel. So now if we simplify, we have 2 times negative 1 squared, which is just 2, minus 5 times negative 1, which is plus 5, and we have minus 7. Okay? And that's equal to a times negative 1 minus 1, which is negative 2. Sorry, I can write that. And negative 1 plus 1 plus 2, which is positive 1. So you'll see on the left here, 2 plus 5 is 7, minus 7 is 0. So it doesn't matter what this is, a is equal to 0. I will show you why a is equal to 0 later, but that means that we basically don't have to count this first factor. Again, I will explain to you why that is the case later, or after we figure out b and c. Okay? So I've moved to another slide, okay, just to give us some more space. But I will start by just writing the equation that we're working with right now. So 2x squared minus 5x minus 7 equals, the first term we calculated a is 0. So the first term is just 0 now. We have plus b times x plus 1 times x plus 2 plus c times x plus 1 and x minus 1. Okay? So we did x equals minus 1. The remaining two terms we have are x equals 1 and x equals negative 2. So if we start with x equals 1, we get 2 times 1 squared minus 5 times 1 minus 7 is equal to b times 1 plus 1 times 1 plus 2 plus c times 1 plus 1 times 1 minus 1. So you can see here again, we have a 1 minus 1 term for c, which will give us 0, which means this term will cancel out. So what we're left with is 2 times 1 squared is 2, minus 5 minus 7 is equal to, we have 1 plus 1 is 2, and 1 plus 2 is 3, so we're left with 2 times 3, which is 6b. So simplifying this, 2 minus 5 is negative 3, minus 10, or minus 7 is negative 10, so we have negative 10 equals 6b. So if we divide both sides by 6, we get b is equal to negative 10 over 6, or negative 5 over 3, if we reduce the fraction to lowest terms. So I'll write equals b, just so that we have this for comparison. Our last term for x is when x is equal to negative 2. And in this case, we have 2 times negative 2 squared minus 5 times negative 2 minus 7. And that's equal to, again, a is 0, so I won't show it. But we have b, which is negative 5 over 3, times x plus 1, which is negative 2 plus 1, and negative 2 plus 2. Again, you see negative 2 plus 2 is 0, so you'll see that this term will just 0 out. Plus c times negative 2 plus 1 times negative 2 minus 1. So 2 times negative 2 squared is 2 times positive 4, which is 8. And negative 5 times negative 2 is positive 10, so that's plus 10 minus 7 is equal to c times, we have negative 2 plus 1, which is negative 1, and negative 2 minus 1, which is negative 3. So we have c times 3. So 8 plus 10 is 18, minus 7 is 11, so we're left with 11 is equal to 3c. Dividing both sides by 3, we get that c is equal to 11 divided by 3. Okay? So now remember, I'll switch colors to make it a little easier to follow. So remember, our partial fractions are now, remember what they were originally, a divided by x plus 1 plus b divided by x minus 1 plus c divided by x plus 2. So a was 0, which means we're crossing that out. I will show you why that's the case after we finish this. B was negative 5 over 3, and C was 11 over 3. So substituting those in, what we're left with is 11 divided by 3 times x minus 1. Sorry, I almost wrote a plus. Plus, for C, we have, oh, I wrote 11 by 3. So I got both those wrong. See, it's easy to make quick mistakes with algebra. So that's why we say to take your time. Obviously, I'm going through this a little quicker, and even you'll see me make a mistake here and there. So for B, we had, remember, negative 5 over 3. So we end up with negative 5 over 3 divided by x minus 1, plus C, which was 11 divided by 3. So we have 11 over 3 divided by x plus 2. So now we substitute those in as integrals. So again, since we have these constants here, I'm going to remove them from the integrals. So what we are left with is negative 5 over 3 times the integral of 1 over x minus 1 plus 11 over 3 times the integral of 1 over x plus 2. Okay? So remember, 1 divided by these functions, the x minus 1, x plus 2, is the ln. So what we're left with in our final answer is negative 5 over 3 times the ln of x minus 1. Remember, the absolute value. Plus 11 over 3 times the ln of x plus 2. Again, the absolute value. And at this point, we can add in our constant at the end. Okay? So you can see here we only have 2 terms. And again, we started with 3. So why was that the case? Okay, so looking back, what we didn't do here is the numerator has an x squared term. You can actually factor the numerator. Okay, so if you do that, it's a little bit different because the value behind the x squared term is not 1. So again, if you want the full details on how to factor this, I encourage you to watch my full video on factoring, but I'm going to give you the Coles notes of it here. So when you have a value before the x squared term, instead of finding the factors that multiply to negative 7, you now have to find the factors that multiply to 2 times negative 7, or whatever the value is behind the x squared term. So 2 times negative 7 is negative 14. So we need to find 2 values that multiply to negative 14 and add to negative 5. In this case, that is negative 7 and a positive 2. So instead of just factoring right away, what you do is you end up writing them out by expanding this equation. So this becomes 2x squared plus 2x minus 7x minus 7. So in this case, now you can factor the first 2 terms and the second 2 terms. So we can take a 2x for the first 2 terms, and we're left with x plus 1. And we can take a negative 1 from the second 2 terms, and a negative 7. And we're left with x plus 1. So factoring this together, we get 2x minus 7 and x plus 1. So remember, our 3 factors were x plus 1, x plus 2, and x minus 1. So if we were to write out the integral, so this integral here, if we were to write it out, we'd have the numerator would be 2x minus 7 divided by x plus 1, or times x plus 1, divided by x minus 1, x plus 1, and x plus 2. So you can see with an x plus 1 in both the numerator and the denominator, they actually would have canceled out. So you could have actually written this as 2x minus 7 divided by x minus 1 times x plus 2. Okay, so it's a step that you don't typically do, you don't have to do. It's not mandatory in order to solve the equation. But just know that you can get a value of 0, and that's likely going to be the case outside of doing an algebra error. Okay, so that's it for this lesson. This was part 1, okay, of doing partial fractions as a method. Part 2 is going to look at slightly more advanced examples, not much more, okay, in terms of what we've done now. The premise of everything will still remain the same. So for these questions, you saw from the examples today, with the 4 examples we did, that there is a pattern in how these are solved. So when you look I encourage you to do these practice problems. Once you pick up on those patterns, it's going to make it a lot easier to know if your final answer seems reasonable. Are you getting the answers that come out with lns? Okay, if you have just an x plus 1 or an x minus 1 term or something like that. Okay, so understanding that will help you a lot. So thanks everybody. If you have any questions, send me an email.